Hey there. Ever wonder why a machine learning model might ace a test in the classroom, but crash during the real exam? Today, we're cracking the code on how models generalize. That is, how well they perform on new, unseen data. It's a big deal, and the math behind it is wild. Let's break it down. So, imagine you're teaching a robot to sort apples from oranges. You show it thousands of examples, and it gets super good at the training set. But then you give it a new fruit, it's confused. Why? Because it didn't learn the rules, it just memorized the examples. That's the problem of generalization errors, the gap between training performance and real-world results. Now here's where things get interesting. The researchers behind this study are using a tool called isoperimetric arguments, which yes, sounds like geometry, but it's really about how probabilities concentrate. Think of it like a balloon. If you inflate it just right, it shrinks to a point, showing how things cluster around an average. This helps them prove that even if a model's errors seem random, they actually hug their average value. The focus: binary linear classifiers, models that separate data with a straight line or hyperplane. These are the basics of things like spam filters or medical diagnostics. The team showed that even with tricky loss functions, like logistic or hinge loss, the errors don't just average out, they sharply concentrate around their mean. So if the average error is small, the real-world error is probably close too. How did they prove this? By using Poincaré and log-Sobolev inequalities, math tools that describe how probabilities spread or clump. These inequalities act like a stability check for models, ensuring errors don't spiral out of control. It's like saying, if your data is nicely behaved, your model's performance is predictable. This isn't just theory. Traditional methods often give loose guarantees, especially with complex data. But this approach is sharp, it's as tight as possible without extra assumptions. That means we can trust models more, whether they're diagnosing diseases, recommending movies, or driving cars. So what's the takeaway? Deep math isn't just abstract, it's the backbone of reliable AI. By understanding how models generalize, we're not just improving algorithms, we're building systems that can handle the messy, real-world data that defines our lives. Thanks for watching, stay curious, and I'll catch you in the next video. Hey everyone, let's talk about a problem that's been bugging scientists for years. How do we make sense of data that's just noisy enough to be confusing? Think of it like trying to hear a whisper in a crowded room. There's signal, but it's buried under chaos. This is what researchers call a weak signal, and it's everywhere in machine learning, physics, and even weather forecasting. So how do you tackle something that's barely there? The answer lies in mathematical bounds. Think of them as invisible guardrails that keep things from going off the rails. Two key players here are these constants called kV and Ku. kV is like a speed limit for how fast things can change, calculated as 4 times this term mx, letter 1d7031, multiplied by a tiny number, 4e-letter 1d7030. Ku is simpler. It's a ratio, z divided by z minus letter 1d7030, but capped at 2e letter 1d7030. These numbers aren't random. They're the rules of the game, keeping the math from spiraling into chaos. Now here's the magic. These bounds let researchers apply two powerful tools, Theorem 1 and Lemma 13, to prove a critical inequality. What's this inequality about? It connects the entropy of a function's squared values, think of entropy as a measure of uncertainty, to something called gamma Roman 3, f, which tracks how much the function wiggles as inputs change. The math gets complex, but the idea is simple. Even with messy data, the system stays predictable. The proof? It's like a tightrope walk. They compare these tricky integrals, essentially sums of all possible outcomes, to simpler terms using functions like g, letter 1d7030, and m_num_x. By sandwiching these terms between lower and upper bounds, they show how the system scales with parameters like letter 1d7030. It's a bit like calibrating a microscope. Too much zoom and everything blurs just right, and you see the details. And here's the kicker. This work guarantees that, with very high probability, like 99.99% confidence, a model's real-world performance won't stray too far from what it shows in training. That's huge for machine learning. Imagine a self-driving car that's been trained on perfect data but fails in the rain. This math helps ensure that doesn't happen. So what's the big takeaway? It's about taming complexity. These inequalities aren't just abstract math. They're the scaffolding that lets us build reliable AI, from medical diagnostics to climate models. They turn uncertainty into something we can manage, proving that even in chaos, there's order to be found. Next time you interact with an AI, remember, behind the scenes, math is working hard to turn noise into insight. Thanks for watching, stay curious, and I'll catch you in the next video.